Okay, so you do have a note card on your semester exam. The keyword here is transformations. That's what I'm looking for. And we need to understand that we are trying to transform this point based off of these transformations. So this tells me that my graph should have a vertical stretch by 3. So remember, vertical means y, like up and down, that is a y value. So that's going to affect this 4. This 4 over here, that we would say that shifts our graph up 4. So I have something that's multiplying to y and something that's adding to y. So the order of operation does matter in terms of what you do first. And then inside the parentheses, right here, I have a -2, which means our graph is going to go to the right 2. So going to the right is going, or left, affects your x value. So this is where we have two different transformations that they're kind of going separately. I'm going to list them separately here as well. Remember, I like to think about this as getting my transformations on my x out of the way first, and then we can think about this as saying just 3y plus 4, right? Once we take care of that x transformation, I don't really care about the x minus 2 anymore. So I'm just saying, how is x being transformed and how is y being transformed? So here, let's look at the x real quick. If my x value started off at 3, and I move that point from 3, 4, so if I look at just that. So here's 1, 2, 3, 1, 2, 3, 4. Here's this point right here at 3, 4, right? And I look at this transformation. One of those transformations is going to take this and it's going to move this over to here. But that's not the only thing that happened, right? This point moved over to the right too, but it also did something else. And those other things are affecting y. So I'm going to go through, I'm going to erase this. So how do I make this move over to the right too? Well, if this is going, if I'm at 3 on like a number line, and here's 3, and I want to move to the right, I'm adding. So I'd be adding 2 to that. So my new x value of my order pair is going to be 5. So that's my change. That's how my x is being transformed. Now I'm going to look at my y's. So this is the same thing. Once again, I've already taken care of this, so I don't care that says this. I can think about this as saying 3y or 3f of x plus 4. And the order of operations does matter because multiplication comes before addition. So now, if I'm looking at my y's, I'm going to take my original y value, which is 4. Oops, let me write this out like this. So I have 3 that's coming from this guy times my y value of 4. And then I have the plus 4 at the end. So that's just 12 plus 4, which is 16. So my new transform point should just be at the point 5, 16. All right, determine if these functions are inverses. One way we can do this is we can do composition of functions, but that's probably not what I would do here in your case. I would just plug them into my calculator and see that they're reflections over the line y equals x. Now, you will have a quadratic that kind of goes over and loops over because we haven't restricted the domain at all. So, but what you will see is something that looks kind of like this. So this would be the graph of this function right here. And then this other one will look something kind of like this. And this will actually come up on this side, but I don't really care about that piece. And these should be reflections over this line y equals x. So if you do that, you can tell that they're inverses of each other based off of that. If you were to plug these in and they weren't, then they are not functions. The other way we could have done this, we could have evaluated the composition, and these would have to equal x. So I could do that, and I can do this, and they would have to equal x. So let me just show you what that would look like real quick since we're on it. So composition of functions, start with the inside. So I'm going to take all of this. Let's do this one real quick. I'm going to plug all of that in for this guy. So I'm going to write this out. So x squared minus 2. Here, let me color code this a little better. So I'll call this orange, and the other one will be purple. So I have the square root of that. And so in for x, I'm going to plug in x squared minus 2. Okay. Now, these are going to cancel inside of there, negative 2 plus 2, and then I'm left with the square root of x squared which just equals x. So that checks, but I'm going to have to do that for the other one as well. So I'm going to have to plug now, I'm going to plug this guy, this whole thing in for that. So if I plug that whole thing in for that, I get, here's my, I'm making that one purple. Here's my x squared minus 2. So this whole thing is going to get plugged in for that. So here's the square root of x plus 2. When I square root, or when I square a square root, that just cancels, and then I'm left with x plus 2 minus 2. Those cancel, and I'm left with x. So because both of these things are true, these are inverses of each other. Okay. Find the inverse of the following function. Swap x and y, and then solve for y. So I'm going to write this as y equals 3x plus 7. And so I'm going to swap my x and y. So this is going to be x. Oh, I totally messed the color coding up on that. Plus 7. So swapping x and y means I would write x equals 3y plus 7. Solving for y, I'm going to subtract 7 from both sides. And then I'm going to bring everything down. I have x minus 7 equals 3y. And then I'm going to divide both sides by 3. Those cancel, and I'm left with the inverse function equals x minus 7 over 3. Okay, here we're asked to find f of g of x on number 4. So the inside function is going to be plugged into the outside function. So I'm going to take all of this, and I'm going to plug that in everywhere I see an x. So this will be the square root of x squared minus 4 for my x plus 6. And that's going to simplify to x squared plus 2 all over the square root. I can't do anything with that, so I'm done. So one thing that I would do is, if you don't know what these are called, I mean, this, you can call that inverse, like on the note card. You can call this inverse. You can call this transformations. This right here is called compositions. So on your note card, if you want to specify that. This one is also called compositions. That's where we see this type of stuff. So here we're given a numerical thing to do, and we always start with the inside piece. So I'm going to plug in a 3 for every x that I see in the function f. So over here I'm going to write this as 3 plus 6 equals 9, and the square root of 9 is 3. So if I know that f of 3 equals 3, then right back over here that says g of f of 3. Well, g of f of 3 just equals 3. So I'm going to replace that. Now this says g of 3. So I'm going to plug in 3, this 3, for my x in function g. So that's at x squared minus 4. This is going to plug in here. Order of operations says I square that first. 9 minus 4 equals 5. Okay, an even function is symmetric with respect to the y-axis, so they have to be mirror images along that y-axis. This would not be symmetric to the y-axis. An odd function, thinking about cubic, they're symmetric to the origin. So if you were to take this and rotate this 180 degrees, you should get the same graph. So in other words, if I look at this as I'm going down, like that kind of squiggly mark is going through the origin. I'm going down in the third quadrant, up in the quadrant 1. If I turn my paper all the way down and to where quadrant 1 and quadrant 3 kind of switch, that would be symmetric to the origin. Okay, X intercepts and vertical asymptotes. Those are rational functions, so you might want to put like rational on your note card. Rational. And we are going to factor because this is talking about denominator, and this is talking about numerator. So we need a factor, cancel common factors, and then simplify. And then write down what's left. Okay, so these are all shortcuts because the coefficient is 1. I'm looking for two numbers that multiply to 10 and add to negative 7. 5 and 2 will do that. They both have to be negative to add to negative 7. Now what multiplies to negative 6 and adds to positive 1? That's going to be 3 and 2. The 3 has to be plus, that has to be minus. These are going to cancel, and I bring down right what's left, x minus 5 over x plus 3. The numerator tells me my x-intercept, so I have an x-intercept at 5, 0, and I have a vertical asymptote at x equals negative 3. That's coming from the denominator. Find the whole of the function. You don't need to tell me the y value, but we're looking for the common factors that cancel. So since I had an x plus 2 in the numerator and denominator, I have a whole at x equals negative 2. I would probably maybe either write down your properties on these next one for logs, or at least write this example. But we want to simplify this expression completely. In other words, I start with 3 logs here. I want to condense those down to a single log with the base 6. So the way we do that is if you have any coefficients in front of the logs, we're going to move those to the exponent. So this guy is going to come up here, and that's going to be log base 6 of 9 squared, which I'm going to go ahead and write that as 81. And then once we have these done, we can just kind of go left to right to look at the sign in between each of those logs. So I'm going to start here in the middle of these. That plus sign tells me that I can condense these into a single log by multiplying that and that. So if I write that out, this is the log base 6 of 162 minus log base 6 of 15. Now the subtraction sign here tells me that I divide these. So this becomes log base 6, and that can't simplify at all. And that's my answer. So this last one was asking us to actually simplify by condensing these. Here we're going to solve these. So we're going to essentially use that same property because we have 2 logs that we start with. We want to end up with 1. So I'm going to look at the sign between the 2. I don't have any coefficients in front. That addition sign tells me I multiply these. So I'm going to rewrite this as a single log. 9 times x plus 4 equals 4. And then to cancel the log, that's where we use this big exponentiating 3. So with respect to the space, that's going to cancel, and I'm going to have 9x plus 36. I'm just distributing this as I go. And then 3 to the 4th power is what that's saying on the other side, equals 81. I'm going to subtract 36 from both sides to get 45. And then I get 9x equals 45. Divide both sides by 9, and we get x equals 5. Quick plug in to make sure that this is not extraneous. If that goes in for here, I have the log of base 3 of 5 plus 4, which is 9. And that works. So, yeah, that's not extraneous. Remember, we can't have the log of anything less than or equal to 0. This is also one that I would try to write down. This is over polynomials. So this is where we had the p over q. So this is our p. That is our q. We would look at the factors of p. So plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. And then we list the factors of q and then put those all together. Plus or minus 1, plus or minus 3. And then I would do all of those together. So p over q. So p over q, I do plus or minus 1. That's coming from these, right? And then I would go this way. I'm not going to write all those arrows up there because that would be confusing. Plus or minus 1/3. Plus or minus 3 over 1, which is 3. Plus or minus 3 over 3, which is 1, and I already have that. Plus or minus 5 over 1, which is 5. Plus or minus 5/3. plus or minus 15 over 1, which is 15, and plus or minus 15 over 3, which is 5, which I already have. So this is P over Q. Given the function, find the zeros. Looking at the factors. Oops, I don't know why I wrote that. That is not that. -1, -2, positive 3. That's from looking at the factors. All right, here's just a matter of like plugging things in and setting it up. So find the amount that results in 750 if 750 is invested. So that's the initial amount. That's our p-value. We're going to be using the compounded interest, which would be this guy. So I'm looking for find the amount, like the total amount. So A equals 750 times 1 plus, we need to make sure we convert this to a decimal, 0.0625 for our rate. That's going to be 12. This is going to be 12. And then after how many years? 5 years. Okay. And then we can just plug that into our calculator. I got, oops. I rounded 0.29 up to 0.3. This one's saying how long. That indicates that you may not be aware of this, but how long is solving for time, which means that we're going to have to use log in here. But it's wanting to know how long it takes for 2,500 to become 10,000. So in the future, our amount should be 10,000. This is what we start with. And it's compounded continuously. So continuous interest is our PERT. So I'm looking for my rate at 0.075 times t. Okay, so from here, I'm going to divide both sides by 2,500. And I get 4. So I'm going to rewrite that over here. 4 equals E 0.075 to the t. I need to bring my t out of the exponent, so I'm going to undo the log. This is the natural log. That's going to cancel these. So over here I have the natural log of 4. I'm going to write that over here to the side. And the natural log of 4 equals 0.075 t. To solve for t, divide both sides by 0.075. Typed it into my calculator. Natural log of 4 divided by 0.075. And I get approximately 18.5 years. These next few are like the ones we just got done doing. So find a coterminal angle. That just means that we need to add or subtract 360 degrees. If I want to be between 0 and 360 and I'm given negative 130, that implies that I need to add 360 degrees. So if I do that, I get 230 degrees, and that is between 0 and 360. Here I want to do the same thing. 5 goes into, yeah, I'm just going to find a coterminal angle. So here I want to go between 0 and 2 pi. 5 goes into 17 more than 3 times, so I need to subtract. And I'm going to make sure my denominator is 5, and this should say 2 pi. So that means my numerator needs to say 10 pi. Because 10 pi divided by 5 is 2 pi. And then this would give me 7 pi over 5, which is between 0 and 2 pi. I want to convert this to degrees. Our conversion factor is, I want pi in the bottom, 180 in the top. So if I convert this, the pi's are going to cancel out. I'm left with 720 over 5, which would be 144 degrees. Convert 305 degrees to radians, so 305. My conversion factor here that I'm going to use is 180 in the bottom now. Pi's in the top. We can do alpha y equals enter. I can write this out like this if I want to, over 180. And then I'm going to type in alpha y equals enter and do 305 in the numerator and 180 in the denominator. And that gives me 61 in the numerator, 36 in the denominator. But I need to make sure I have my pi there. Okay, on these types of problems like this, where I ask you to write an equation, the easiest thing probably to do on a multiple choice test is just to plug those equations into your calculator and match it up with the graph. But I'll remind you how to do this when we do this type of stuff in class. First of all, we're looking at the zeros. So I have one at 0. So I have an x-intercept at 0, and also at 0 I'm bouncing. So what does that mean? That means I'm going to have a multiplicity of 2. I also have one at positive 2 where I cross, and I have one at positive 3 where I cross. So now when I go and write this out, I should get something that looks like this. Well, these other two factors, if I have an x-intercept at 2, that means x minus 2 is a factor, and x minus 3 is a factor. Then I have one at 0, that needs to be just x is a factor, and that has to be squared because I'm bouncing. Also, my end behavior is going straight up, so my degree should be even, and which it is. There's 2 here, 1 here, 1 here, and they're both going up, and it's a positive leading coefficient. All right, here we're looking for the limit as x approaches 2 from the right. So as we come from the right this way, we are going to positive infinity. So this one right here, we would say is positive infinity. And as we approach 2 from the left, we're going down to negative infinity. All right, and then the last one, you don't have to worry about because that's in Unit 8 when we get back from the break. Good luck.